We are working on the optimization process. This is part 2. The list you see in front of you is a common sense list of things to do to work through these problems. Of course, reading the problem, identifying what you want to maximize or minimize, draw a diagram, devise a formula for the quantity that you want to maximize or minimize, identify any constraints and use these constraints to help you find additional equations to substitute into your formula so that it contains only one variable, and then solve using the process that we've been using in calculus for determining mins and maxes. Check your solution and state your conclusion as a clear sentence. Let's look at an example involving optimizing fencing. We want to enclose a rectangular field with a fence, and we have 500 feet of fencing. So immediately we're thinking to ourselves, well, here's a constraint. And also there's a building on one side of the field, so one side isn't going to need any fencing. We want to determine the dimensions of the field that will enclose the largest area. So reading the problem, we see that the perimeter minus one side must be 500 feet. And we want to maximize the area of the field, so the area. So this is similar to our tabletop exercise. We'll draw a diagram, and that orange bar across the top is supposed to represent the building. So we're actually not including that fourth side in our calculations. And the formula, well, you already know the area. And constraints. What are our constraints? Well, that 500 feet of fencing is a pretty big constraint. That means the perimeter, but not exactly the perimeter all the way around. Just the perimeter on three sides has to equal 500 feet. If we solve that for y, we'll get a value which represents our constraints, and then we can plug that into the area, which very conveniently gives us a formula for area that just has one variable. Also, we know that x can't be, of course, any less than 0, shouldn't even be 0, and it can't be any greater than 250, otherwise this situation is not going to work. All right, so we have everything set up. We've got our formula, and now we want to find a max of the function a. Now we resort back to that process that we've used before. We're going to find the first derivative. We're going to set it equal to 0 and solve. So this gives us a dimension for our x, whatever you've called it, of 125 feet. But we have to see, is that a max? So using the closed interval method, since we have a closed interval, we need to check that critical number, 125, along with the endpoints, 0 and 250. So, well, yeah, just as we suspected, the area when x is 125 is going to be the largest of the three values that we've tested. And now we can solve for y. It turns out y is 250. So, oh my goodness, x is 125 and y is 250. And those are feet. So it looks like if everything still fits into our constraints, and that's just kind of a double check, make sure no arithmetic went wrong anywhere. And we'll write our conclusion as a grammatically correct sentence. So given that we must fence three sides and we have 500 feet of fencing, the dimensions yielding the largest area are 125 by 250. Stopping now, and I'll move on to recording 3 to do the next example.